Let's start now with lecture number 10, and this is about file systems. So you have the reading instructions here, as always, from the book we use in the course, and also the extra facultative reading if you want to have a look. So this lecture is about file systems, and I guess at least some of the concepts we will discuss here, you should be pretty familiar with them. There are two things that are very connected to the file system that you see and use every day, and that would be files and directories. So I think this lecture is sort of easier than others because some of the concepts you should be very familiar with them. But nonetheless, the objectives of this lecture are to explain the function of file systems and also which interfaces we have. We will discuss, of course, trade-offs, as always, when it comes to how we manage the file system, maintain the information, and so on. We will discuss protection mechanisms that are defined in the file system, and also different ways in which you can actually allocate the information on disk and also keep track of which parts of the disk are free if you have to write something new and which are already taken. So this is the agenda. Let's go one step at a time. So let's start with the first part here, file concept. So what extra information, what overrides, interfaces does the operating system needs to provide in order to provide files and directories, such type of abstractions to the users. And let me say something before we start. So now we have discussed memory, different allocation schemes, and also virtual memory, and all these concepts in the last two lectures. So you will see that there are parallelisms between what we discussed in those lectures and what we are going to discuss today. But there are also aspects that are very specific to the file system. So a file, if you want to give a definition for it, it's the minimum allocation unit for the user. When the user decides to store something on the disk, the minimum it can store is a file. This is the abstraction that is introduced by the operating system. And the idea here is to give this high-level abstraction that is the file, so that the operating system under the hood takes care of all the extra steps and the interactions with the hardware, you know, all this we mentioned from the very beginning of the course, all these ugly interfaces that you don't really want to talk to directly, but that you can just interact with through the operating systems. Again, there is a separation between logical and physical representation, and this is, again, thanks to this abstraction that is the file, and similarly the abstraction that is the directory. And you already know that it's not just an abstraction, the file. Actually, each file comes with metadata that is both for the sake of the operating system, but also for the sake of the user. Okay, you have different types of files. Some are text files, you can have binary files, some are about programs that can be run, and so on. Now, one thing that is important to understand here is that for the majority of files, what the file is and what the computer should do to interact with such a file is actually defined by who creates the file. So if you double click a text file and Microsoft Word opens up and you can text on it, it's because there is a quite complicated, complex series of steps in between, and these exist because some of the metadata associated to the file says this is a text file, and the operating system associates text files with specific programs, so that actually when you want to open a file, what you do is not just opening the file, but rather telling the operating system to start a specific process and then pass that file to that process, because somehow it has been registered at the operating system level that this specific file, let's say a text file, is usually managed read, written, modified with a specific program that needs to be into execution. It needs to be brought up into execution before you actually access the file. Some of these things are done with this metadata that we have in the files that are the attributes of the file, okay? Of course, you have the name. I'm saying simple stuff here. You have identifiers. You have different types. For each file, you need to keep the location. So actually some information that allows the operating system to go and read in the specific position in the disk where the file is stored. You have the size, you have different protection levels. You might read the file or execute the file depending on what attributes or how the protection attributes are set. And you have time, date, and other identification. So again, pretty simple what I'm saying, and I don't think I'm saying anything too complex here. But if you think, for example, at the process of compiling a lot of C files so that you create a binary, you probably know that when you compile your project, you don't necessarily recompile all the files, but you might compile only the ones that have changed since the last time you compiled. This is a good thing because it requires less time to for you to compile something. But now you probably see that if you have such a feature, it's because of the attributes you have in the file. So you have an attribute time, and the process you run to deal with text files that contain instructions when you want to make them into a binary can also use these attributes like the time, so that you can check what is the time at which the last binary was or the last compiled version of the file was created. You can check what was the time it was modified last, and depending on this, it can decide whether it's the case that the source file needs to be compiled again or not. So you can see there are a lot of things happening thanks to the metadata, the attributes you have for each file. Here you have a list. I don't think I need to go through it. It's pretty simple, but basically it's what I said before, that each file has an extension and the operating system knows what to do with each file, also based on the extension you have. So it can associate different processes that should be started before you actually operate on the file. Now, the operating system gives you a lot of functionality to operate with files. It's not just the abstraction per se. The operating system, of course, needs to maintain extra information as always to allow for this functionality. And as we saw when we started discussing processes, some information is specific to individual files or individual processes, while other information is global. It applies to the entire system. The operating system keeps an open file table which tracks which files are open, pointers for each file, so that if you are doing a sequential read, for example, you can keep track of the last thing that was read or written to a specific file. It needs to keep a counter for each file. Imagine different processes are reading from the same file, then the operating system might read the file only once from disk and then give this to several processes. But if one of the processes closes the file, it doesn't mean that the file should be removed from the memory. There could be other processes that are still reading the file, and this is why the operating system has also a count for each file. It keeps the location on the disk. This is clear, the access right, and several other things we will see now during the lecture. So again, in summary, we need extra information. Some is specific to the file or to the process that you are using to interact with the file. You, in this case, is the user or the programmer. And then some information is global and it applies to the entire system. It gives you, of course, also functionalities to operate on files. Okay, you can create, write files at specific locations. You can read files. You can reposition within file. You can go at different offsets inside the file. You can delete files, truncate files, and so on. And everything looks pretty simple. I don't think I'm saying anything too fancy that is too fancy here. But again, at this point, you should probably have this feeling that actually opening a file requires a decent amount of steps. You need to interact with the disk. There will be system calls. You need to locate where the file is on disk. You need to read something and associate with the process. The process might be in waiting state, so you need a mechanism to decide where to put what you are reading. You might be swapping out processes, and if you swap out processes that are waiting for stuff from the disk, then you should keep these things that are being read from the disk in a specific location so that it doesn't affect, they are not affected by the fact that you are swapping out processes and so on. Here we can just look at a very simple example. So this is a program that copies a file. You give the input file and you specify where it should be, or the destination where you want to copy the file. I ask you to go through this code and basically check it. It's not complicated, but what I'm trying to say here is that, you see, when you say open read only, and you specify here, for example, the location where the file is, this is actually resulting in a long and complicated series of steps. And all these things are done by the operating system, and they simplify your life because it's not you who has to interact directly with the disk to specify in which blocks we will see what these are, the file is stored, whether it is contiguous blocks, whether it's scattered around the disk, and so on and so forth. Okay, I'm not going now through the pseudocode. Have a look at this point. It should be pretty clear. Again, here you have this read, write, close the file, and so on.